Welcome to the university. In this video we will discuss the three types of electrical circuits. We will also teach you how to solve for total resistance in a series connection, including the ways on how to solve for the total resistance in a parallel connection, how to solve for the total resistance in a series parallel connection, and how to solve for any electrical quantity in simple electrical circuits. A basic circuit has three main parts: a source of energy, also known as voltage source, a closed path or conductors for the current to flow, and a device which uses the energy, also referred to as electrical load. If any part of the circuit is open or missing, the device will not work. There are ways to wire circuits. There are two basic ways to wire a circuit. The other method is just the combination of a series and parallel connection. Before we introduce the ways to wire a circuit, keep in mind that a resistor could be anything, for example bulb, toaster, ceramic material, and other materials. Resistance. The first type of circuit connection is called a series connection, in which resistors are connected one after another. This is sometimes called the head-to-tail connection. The second type is called the parallel connection. You will see that in between a set of junctions, resistors are connected parallel to each other. All heads are connected and all tails are connected at one end of each junction. When studying electrical circuits, one must be familiar with the electrical symbols used in making circuit schematic diagrams. We introduce some basic but very important symbols used in circuit analysis. Schematic symbols. Before you begin to understand circuits, you need to be able to draw what they look like using a set of standard symbols understood anywhere in the world. For the battery symbol, the long line is considered to be the positive terminal and the short line denotes the negative terminal of the battery. You also need to familiarize yourself with the measuring apparatus or monitoring device used in circuit analysis. We introduce the voltmeter and ammeter. They are special devices you place in or around the circuit to measure the voltage and current. The voltmeter and ammeter. The voltmeter and ammeter cannot be just placed anywhere in the circuit. They must be used according to their definition. Since a voltmeter measures voltage, or potential difference, it must be placed across the device you want to measure. That way you can measure the change in voltage across the device. Voltmeter is drawn or connected across the resistor. Since the ammeter measures the current or flow, it must be placed in such a way that it can sense the flow of charges. It is connected in series where the charges go through the device. Current goes through the ammeter. Simple circuit. When you are drawing a circuit, it may be a wise thing to start by drawing the battery first, then follow along the closed loop starting with positive and drawing the symbols of your circuit elements until they form a closed path back to the negative terminal of your battery. You can see such a diagram below. We will now explore series circuits. In a series circuit, the resistors are wired one after another. Since they are all part of the same loop, they each experience the same amount of current. In the figure, however, you see that they all exist between the terminals of the battery, meaning they share the same potential difference generated at the end of the terminal of the battery. It is also true if we say they share the same voltage. We see that there is no other way for electrons to pass through, and they must pass through each resistor. Hence we can say that the current in the series circuit is the same across every resistor. We say that I sub t is equal to I sub 1, is also equal to I sub 2, and is also equal to I sub 3, and so on and so forth. As the current goes through the circuit, the charges must use energy to get through the resistor. So each individual resistor will get its own individual potential voltage. We call this voltage drop. Using Ohm's law, this voltage drop is equal to V is equal to I times R. We sum up all the individual voltage drop across each resistor to get the total voltage, V sub t. So we have V sub t is equal to V sub 1 plus B sub 2 plus B sub 3, and so on and so forth. This is also equal to V sub t is equal to I times R sub 1 plus I times R sub 2 plus I times R sub 3, and so on and so forth. We know that we have a constant current flowing in a series circuit, and therefore we can factor it out. We will have V sub t is equal to I times the quantity of R sub 1 plus R sub 2 plus R sub 3, and so on and so forth. We have the formula for the total voltage in a series circuit is equal to I times the summation of all the resistance, or I times R total. We also found out that the total resistance in a series circuit is equal to the sum of the individual resistance present in the circuit. Note, they may use the terms effective or equivalent to mean total. We now try to apply the concepts that we have learned. See the sample below. A series circuit is shown to the left. We add the individual value of each resistor and we will get 6 ohms. What is the total current flowing in the circuit? We apply the formula I is equal to V divided by R, and we will get 2 amperes. Since we know that in the series circuit, the current is constant through all the resistors. What is the voltage drop across each resistor? For this question we apply Ohm's law to each resistor separately. We will see that the voltage drop across R1 is 2 volts, for R2 is 6 volts, for R3 is 4 volts. Notice that the individual voltage drops add up to the total. We now discuss parallel circuits. In a parallel circuit, we have multiple loops. So the current splits up among the loops with the individual loop currents adding to the total current. The voltage across every resistor in a parallel circuit is the same as that of the voltage source. It is important to understand that parallel circuits will all have some position where the current splits and comes back together. We call these junctions. The current going into a junction will always equal the current going out of a junction. The amount of current flowing in a junction is equal to the amount of current flowing out of the junction. In a parallel circuit, we notice that the junctions both touch the positive and negative terminals of the battery. That means you have the same potential difference down each individual branch of the parallel circuit. This means that the individual voltage drops are equal. We have the formula V total for a parallel circuit is constant and is equal to V sub 1 is equal to V sub 2 and is equal to V sub 3, and so on and so forth. We also notice that the current is different across each resistor. We can sum it up to find the total current. We can use the Ohm's law to get the current in each resistor. We will find out that the total current is equal to I sub 1 plus I sub 2 plus I sub 3, and so on and so forth. Using the Ohm's law to show that the total current in a parallel circuit is also equal to the total voltage, V sub t divided by the total resistance R sub t, and this is also equal to V sub 1 over R sub 1 plus V sub 2 over R sub 2 plus V sub 3 over R sub 3, and so on and so forth. And then we use the fact that the voltage is just equal across each junction, and hence we can factor it out. We can now use this to find the total resistance in the circuit by dividing both sides of the equation by V sub t. Notice that this is in its reciprocal form. We can now apply these concepts in the sample problem below. To the left is an example of a parallel circuit. A. What is the total resistance? When we apply the formula and solve for the reciprocal of 1 over r sub t, we will see that it is equal to 2.20 ohms. The next question is, what is the total current flowing in the circuit? We use the formula for the Ohm's law. V is equal to I times R, and we will see that the current is 3.64 amperes. What is the voltage across each resistor? It is 8 volts each. We can also try to find the current in each resistor. We apply the Ohm's law individually to each resistor and find out that the currents are 1.6 amperes, 1.14 amperes, and 0.9 amperes for R1, R2, and R3 respectively. Also note that individual current adds up to the total current. We can also combine series and parallel circuits to make a compound, otherwise known as complex circuits. Many times you will have series and parallel in the same circuit. See the example below. Solve this type of circuit from the inside out. What is the total resistance? We will try to simplify the complex parallel circuit and find out the equivalent resistance that can be added to a series circuit. We will see that the circuit above is also equal to the circuit below. We just have to add the values of the resistance and we will see that it is equal to 113.3 ohms. And we can also find out more about the circuit. Thanks for watching. See you again here in the university.